So the aim of this week's lecture is an introduction to water. Next week, we're also going to have another introduction or second lecture on water. So please make sure that you look at those notes in conjunction with these notes. First of all, some basic ideas of water that I hope you all know. Water is a 2-hydrogen-oxygen bond molecule that is at an angle of 105 degrees. It has a low molecular weight. There are various other charges, and I'm not going to read through these slides. And the idea of this presentation is mainly that if you want to, you can pause and you can read through the things as needed and move backwards and forwards. So I don't want to spend too much time reading through everything when you can do that yourself. More importantly, though, water is a global phenomenon. So we have water in the water cycle where it evaporates from the sea, it forms clouds and falls down onto the land, where it then runs through the rivers, dams. We can then catch it and use it, and it flows back into the sea where the whole cycle continues again. How much of this are we capturing for ourselves? As you can see on this slide here, that evaporation from the sea or the oceans constitutes the majority of the water in the water cycle. It then unfortunately falls straight back into the ocean, but some of it does blow over the land, and as you can see there, precipitation and the vapor transport from the clouds then goes along, and some of it does rain onto the land, where some is then caught in lakes, which we can then use. So please remember, we had in the first slide, sorry, not the first slide, the first lecture, how much water is actually available to us. And you'll remember most of it is caught up in the sea and the oceans. Some is available through lakes, but we get a very small fraction of this water from the water cycle to be able to use for our daily lives. Where does this water land, though? And as you can see, this is a soil moisture graph, or not graph, sorry, map. And most of the water avoids Southern Africa. So the blue and the green sections are where there's lots of water, soil moisture. You can see in the equatorial areas in the middle of Africa, as well as the rainforests around Brazil, there's a lot of water in the soil. South Africa, we have very little water in the soil. You can see the same thing, global water consumption. If we see this in terms of who uses water around the world, the top graph here is the world, then Asia. We go all the way down to the bottom one in terms of Africa for who uses or how much water is consumed by regions in billions of cubic meters per year. Obviously, the lower one of Australia and Oceania countries, that is almost none because there are few people there. South America also is fairly water scarce. Let's just back a slide. I can't jump back a slide, sorry. Go back in the video and see there was some water scarce areas there as well, so in South America. Africa, though, we are still quite low compared to the rest of the world. In South Africa, or rather in Johannesburg, what are the water demands that we have as a city? So this is Rand water. This is looking at what the water consumption would be in South Africa from 1905 to 2025. The pink line is the actual water supply, and you'll see this goes up until 2005. And then from 2005, the projected water use is actually increasing, not quite exponentially, but it's probably linearly. It's quite a sharp increase compared to some of the other times in our history when the water use wasn't as high. That water use or water use in general can disappear fairly quickly. So the table that we've got here shows us some household water usage numbers as well as some agricultural items here, and you can see that in liters of water use every time you flush a toilet, and obviously depending on the toilet that you've got, it can go from as low as 6 all the way up to 30 liters every time you flush the toilet. Washing a car with running water for 20 minutes, you're using 800 liters of water. So you start adding these up for every household, for every person that lives in Johannesburg in South Africa, it comes to quite a lot of water. One of the numbers that I want to just quickly point out down here, 1 glass of milk. You look at that glass of milk and you think, how on earth are we using 380 liters of water when we have 1 glass of milk? So these numbers are from what's called a water footprint, and we'll get to this water footprint study in one of our later lectures in the course. But the idea is that this 380 liters of water, just as I say, the example for milk, is not just from the milk. Obviously, there's very little water in that 1 glass of milk. It's less than a liter. But all the water that comes from watering the grass or the the irrigation of that land, the cows then drink water. There's all sorts of water involved for the cow and all the processing that's involved for getting the milk, washing the bottles rather, to getting the milk into those bottles. And that total equals 380. So that's an absolute, not an absolute number. It's a what do we call it? It's a virtual number as well as a real number. because that dirty water is then going to be thrown into rivers, and that rivers then pollute the streams and other water sources. And later in the course, as I say, we'll show you how that number actually gets calculated. 1 pound of cotton, though, it's one of the more famous examples where cotton is very water intensive. It's 7,730 kilograms. Sorry, not kilograms, liters, or same thing, liters of water for 1 pound of cotton. Again, as I've already said, water is not abundant in South Africa, and the average rainfall is only 450 millimeters per year, where the world average is not quite double, but it's 486 millimeters per year. So that's the amount of water that if it would fall onto the ground in a flat open area, it would accumulate to a height of 860 millimeters. In terms of our rivers in South Africa, we have very few and small rivers compared to some other countries like the Amazons and the European rivers, where they're actually large enough to navigate ships down of them. In South Africa, as the example we've got here, all South African rivers carry less than half of the water compared to the Zambezi River. So the Zambezi River, one river alone, carries more than double all of our rivers in the whole country. We have the Vaal River, which is economically important for us. It is the biggest dam or the biggest supplier of water to Gauteng for us up in the Highveld, even though it is relatively far away from us. Johannesburg has a unique feature about it, that there is no large water body around it, whereas most cities in the world are either on the sea or on a large river. So Johannesburg rather is quite unique in that point, that we are far away from any water source. We also have few aquifers, so there's very few water in the ground. And the water quality management is therefore a very critical skill, or very critical requirement rather, in South Africa to be able to manage such scarce resources. Just to let you know, where does our water then come from? So we have something called a drainage basin, which is also called a catchment area. So that is an extent of land where water or rain, so any water in the environment from the water cycle, as we said, from the rain falling on the lands, will fall into an area and where it all groups together. So you can see obviously the higher and lower lying land areas, If we look here, all these rivers will then flow together. So this red section is all part of the same catchment area. So there are, I think it was 19 areas in this. I stand to be corrected. I think it's coming up on a future slide. Different areas where the water catches. So you remember your geography from high school. The Drakensberg mountain range comes through the middle here. So that's why some of the catchment areas fall down to the Indian Ocean to the right, and the others are going towards the Atlantic on the left. In South Africa, we also have water management areas. So the country is divided up into different water management areas. These are not the same as the catchment areas. So if you ever come across the water management area, it's not the same as the catchment area or the drainage basin. In terms of the South African water management principles, it's generally designed around 3 pillars. The 3 pillars being sustainability, equity, and efficiency. So obviously the sustainability is a term that we've come across a couple of times here, and the sustainability being again to promote the social and economic development. So it's that sustainability triple pillar again, but at the same time they must also be protected. So sustainability meaning that whatever we have today, we need to also have for future generations. Equity, obviously every citizen needs to have the same amount of water. It shouldn't be fair that somebody with more money can buy more water, or somebody can buy the rights to water over somebody else. And then lastly, obviously efficiency. We obviously don't want to waste any water because it's such a scarce resource in the country as it is. We want to make the best use of our water resources. In South Africa, there are going to be 2 main pieces of legislation that are going to influence water. The first one is the National Water Act. So National Act meaning that it comes from the highest levels of government, and in this instance it's through the Minister of Water and Sanitation. For these slides and for everything that I'm doing now, I've tried to refer to it either as a department or a minister, mainly because, as many of you know, the departments change hands every now and again. So it used to be the Minister of Water and Forestry, or Water Affairs and Forestry. It's now the Minister of Water and Sanitation. So when you look up and you see old notes online, or if you see other things on the internet, just note that the Water and Sanitation used to go by a different name. Okay. This act, the National Water Act of 1998, recognizes that different user groups need access to different water in different ways. It's also there to protect water through an integrated water resource management. Okay. One of the key issues with the National Water Act is that through it and the department sets the amount of water that is allowed or that should be kept aside for basic human needs. So there are going to be basic human needs as well as other users such as agriculture and other needs that are going to require an allocation of water. The amount of water that is kept aside is going to be called the reserve. The National Water Act also has various other issues that are revolved around it, which I will let you read on this slide, as well as on this slide. So there are various catchment management strategies that you can read through and just see how this Water Act is applied. Getting back to the reserve, though, the reserve includes the amount of water for basic human needs, this bottom portion in this river diagram here, as well as the ecological needs. That makes up the reserve. So that is, as we said, is set by government or the Department of Water and Sanitation. There's also a section above that in the river or in the allocatable yield. So this extra set, the government says who is allowed to use it in terms of international obligations, strategic needs, or anything else, as well as other uses. So these other uses are going to be left up to each catchment management agency which is responsible for it, and that could be for agriculture, for mining, or various other uses as they deem necessary. In terms of water, not only are we short of water, but in South Africa, you'll see we also fit into this pink area at the bottom, meaning that water is very expensive in the country. This is relative to the mean household income as well as the cost of water. So because we are a fairly poor country, water is expensive in most of Africa. We can see this again here in Africa, and I'm put on the spot now, so I can't find South Africa, but we can see in these gray areas, all of these gray areas are African countries. All of them are low income houses as well as cost of water. Some of them are going fairly high up to the right. So we are poor and it costs us a lot for water. The last thing in terms of the National Water Act is that there are financial drivers as to why this act exists. We want pollution control as well as prevention of overuse of resources. So the financial aspect of this is that the water pricing strategy comes through this act as well as the department. Nobody can just take large amounts of water out without authorization, so the water use licensing is also part of the department's responsibility. This license is the legal document which is renewable every 5 years up to a maximum of 40 years. Future issues which might influence these water tariffs include water resource management charges, the cost of water discharge systems, as well as various other items as listed in front of you. The second act which will be important for water is the Water Services Act. This one is more for a municipality in order to assist them to undertake their role and look after the interest of us as a consumer. It also provides a right to access of basic water supply and basic sanitation. So as we said in our law lecture, that there are certain things that the Constitution provides to us, and the access to basic services will be one of those items in the Constitution, as well as this Water Services Act. In Johannesburg, we've already said that it is Rand Water that is accountable for the water distribution, and that the Vaal Dam, as well as the Sterkfontein Dam, are the main suppliers of our water. In Johannesburg, compared to many other areas in the world, the drinking water, and that's referred to as potable, so potable water, the quality of that is very good in South Africa, and well, in Johannesburg in particular. The one concern, though, is that we have a large loss of water. So unaccounted water loss in South Africa is as high as 42%, whereas the international benchmark is typically down to 14%. So that is from water that is broken pipes leaking into the roads, as well as sometimes other unaccounted for losses. This can come through, as I said, broken pipes and things like that, but also illegal connections and other items that you might be able to think of yourselves. The challenges facing the water sector in South Africa in particular include things like poverty, access to water, and the impact of the economy on water. So being a poor nation relative to, or a third world developing nation, water is, as we've already said, very expensive. Are there ways that we can reuse the water because we've got so little of it? How do we manage the demand for this water? And what happens when we start getting into international water wars or regional water wars? Cape Town recently had a large drought, and things didn't look very good for them. They were restricted to 90 liters of water per day. If you go back to the slide that we had on how much water you use per day, you'll see that 90 liters of water gets used up very quickly. It's effectively 3 flushes of a toilet if you have a poorly operating toilet, as per that previous slide. So should we as a country, and this is a regional water war, should we have sent water down to Cape Town from Johannesburg if we had enough of it, if we had an excess? How do you actually do that logistically? How do you allocate the water between Cape Town and Joburg, if that's the example that we're using here? What happens if it becomes international? So things like this are serious challenges that could face South Africa in the future, as well as obviously the impact of the water quality, and how do we engage the public to actually get this as something that we move forward with. Before I carry on, just some definitions that we need to look at on some of the water quality definitions. The first one is abstract, which simply means take out. Discharge is putting back in to the environment. Water pollution, I think we should all know, it's when the water has some pollutant in it, so there's a presence of a harmful chemical or any contaminant. And wastewater is discarded or previously used water from a municipality or other industry. So sometimes that is divided into municipal wastewater or industrial wastewater. What do we look at in terms of water quality characteristics? And there are several different qualities that are all governed, or we can all check them through the SANS 241 standard. So if you look at that, it will tell you how to complete a water check. The main items of this are VOCs, SOCs, IOCs, BBPs. As I mentioned before, there are going to be a lot of acronyms in this course. I'm going to leave this one to you to go and look up what each of these are. Some of them you probably already know, and then add them to the document that I've been building up on the OneDrive notes so you can see if you're right on those ones or not. I will add them as well in the next few days. Those form the chemical quality characteristics that we need to monitor. They're also biological ones, so we don't want microbial contamination. We also have physical characteristics, so the water might be low on chemicals or biological contaminants, but it still might be a foul or have a foul smell or a different temperature or taste. It might taste funny, and all of those might make it unsuitable for human consumption. I see this one on temperature here, and just as a note, I've put a second set of several documents on the Canvas, the Ulwazi page, and one of them indicates what sort of wastewater treatment, or if you discard wastewater back into a river, what levels of contaminants can you have? And one of them listed here, as well as in that document, is that the temperature cannot be more than 3 degrees Celsius higher than the temperature that you are putting it into. So obviously, if you put a higher temperature or other chemicals into a river, you are probably going to kill the fish and the other wildlife, which we don't want. So here is an example for the Western Cape. What are the general limits for wastewater? So in the Western Cape, and this is just the one that I've got up on the slide here, we can find ones for other areas of the country as well. There is a limit for pH, chemical oxygen demand, conductivity, ammonia, and various other things, which you need to abide by when you discharge wastewater. When you discharge wastewater, we are then going to have 2 types of decomposition. So the first one is aerobic decomposition, and the second is anaerobic. The difference between these two is that in aerobic, we mean air, and in chemical reactions, hopefully you remember that oxygen is the reactive portion of that, and in anaerobic, there is no air. So you'll see it's again organic matter and microorganisms, which is the same as the first slide, but this time there is no oxygen. From that, we can then break it down into carbon dioxide, water. The microorganisms will grow, and we have stable products coming out as a result of aerobic decomposition, what's often called aerobic digestion as well. Anaerobic digestion or decomposition, you will have unstable products such as H2S and ammonia, as well as methane, and these often smell, so you can have a bit of a smell coming off these things. These, because they're unstable, they often can break down. So maybe not these ones, but if you have carbon monoxide and other types of gases coming off, those may break down, as well as any other volatile organic carbons. When we look at the water quality, there are a couple of characteristics that are going to be important that we want to investigate. The first one is dissolved oxygen. The next 2 are the oxygen demand, either biological or chemical, and it's often referred to as BOD and COD. Suspended solids or dissolved solids are going to be important, as well as the nutrients, pathogens or viruses, as well as any metals, and we've already said taste, odor, temperature, and color in terms of water quality. For this course, I'm only going to ask you, and you only need to worry about the biological oxygen demand when it comes to actually calculating numbers. So in this week's TUT and the examples that we'll briefly just skip over later in the slides, please make sure that you can calculate the biological oxygen demand for a wastewater stream. However, what is dissolved oxygen? So oxygen from the atmosphere can dissolve into water, and water holding a can hold a limited amount of gases, which then can diffuse in or out of the water. If there is a lack of oxygen and we have an anaerobic environment, so we've already said that anaerobic is when there is no air, the fish will die and the algae will grow. So you get plants that thrive when there is no oxygen because they like the CO2 to grow, but unfortunately the fish die and we'll get an imbalance in our rivers and lakes. In order to measure dissolved oxygen, you're simply going to use a handheld probe, which you're going to put into the water, and you'll be able to measure dissolved oxygen. So it's a similar tool like a pH meter that you've used in chemistry before. So because of that, I'm not going to ask you questions on calculate a dissolved oxygen for any sort of exam or test questions for this course. The biological oxygen demand is a measure that measures the rate of oxygen consumed by microorganisms as they decompose organic matter. So we've got the word here, microorganisms. Just do this right. So microorganisms, that's where the biological part comes in for the oxygen demand. So how much oxygen do the microorganisms require? And that is the measure BOD that we're looking at here. It can be estimated from stoichiometry of pure water systems per the decomposition of CO2 and water. This calculation we'll get to in a slide or two's time, and this calculation for BOD, I do need you to know for tests and exams. If we have a low BOD, so what it is used to measure treated wastewater before we discharge it. If we have a low BOD, it means there's no contamination or available microorganisms can't use the available organic matter. If there is a high biological oxygen demand, it can be harmful when placed in the water body because that high oxygen consumption rate, because these microorganisms are consuming all of these organisms, all the organic matter in the water, it will lead to an anaerobic condition. And as we said previously, as we have anaerobic conditions, we will have no water, or we'll approach zero dissolved oxygen in the water system, which will be bad for the ecosystem. Typically, we measure this over 5 days, so you'll refer to this as the BOD5 in the dark at 20 degrees Celsius. So we don't want any algae growing because of light. That's why it's the dark. And 20 degrees Celsius is just the standard temperature that we use. We're looking at the 5-day measurement for the measurement of oxygen consumed, because if we had to wait forever, the ultimate BOD test is going to be time consuming. And because of that time consuming nature, we typically will only look at the BOD5 value. In order to calculate this, so as I say, this is the calculation that you need to use to be able to do, and this is in the textbook. So this diagram comes directly from your Masters in Ella textbook. There are 2 types of tests. The first one is an unseeded test, so you don't add anything to the water, and the BOD5 is calculated by the DOI, the dissolved oxygen at the initial stage, minus the dissolved oxygen at the final stage. So we said the biological oxygen demand is simply how much oxygen, the demand for oxygen, so the difference from the initial to the final would give us that number. If we need to, we would divide it by P, where P is a dilution factor. So if we dilute it, what is the volume of wastewater divided by the volume of wastewater plus the diluted wastewater, dilution water? That will give us the P, just to factor that in. A seeded test, we are going to have a seed dilution. So we have nutrients in the water that we then add to the blanks and to the other system. As I say, please go and read up on this in the textbook. That calculation is now the same first part, the dissolved oxygen initially minus the dissolved oxygen final. We now minus a BI minus BF, where that is the initial dissolved oxygen in the seeded dilution water. So that's going to be the water that we then add to our test sample, minus the amount of dissolved oxygen, B, in the final diluted wastewater. Again, we then have to multiply by a dilution factor, 1 minus P, and divide everything by the dilution factor P as well. Examples, so I'll let you read through these examples. These are very similar to the ones that I've given you in this week's TUT on how I could test you on this. The chemical oxygen demand is slightly different to the biological oxygen demand in terms of this is the total amount of oxygen required to oxidize organic matter. This can be used to estimate the amount of organic matter present in a water sample. So it's similar to the BOD, but for this course, as I've said before, we are not going to worry about COD in terms of how do we calculate it. In terms of calculating, though, if you had to know this for future reference, we are going to use a dichromate, which is used as the oxidant, and the results are then expressed as milligrams per liter of oxygen, of O2. The amount of the dichromate used is expressed in an equivalent amount of oxygen. Solids are also going to be an important part of wastewater or water quality, and the first thing that we are wanting to do is to evaporate the water sample at 103 degrees Celsius so that we have complete evaporation. We don't want to wait at 100 degrees Celsius. We want to make 100% sure that the sample is dry and how much residue is left over. What is the weight of the residue that's left over? We can also classify the wastewater solids by their size. So anything less than 10 to the negative 6 millimeters, so please note this is in millimeters, so this is really small, is going to be dissolved solids. Colloidal between 10 to the negative 6 and 10 to the negative 3. Suspended when it's greater than 10 to the negative 3. And it is settlable when it's greater than 10 to the negative 2. Remember, that's 10 to the negative 2 millimeters. Suspended solids are going to be one of the important aspects of the solids in this one, as they are undesirable in water. Because they are suspended, they could settle out, and when they settle out, they could cause deposits. So you get a sludge at the bottom of dams and lakes. That settling can also cover habitats of either the fish or any other wildlife, particularly of the eggs. As I already said, it can form a sludge. It can also have an organic component to it, which could serve as a food source for microorganisms, which then grow and they start developing the pathogens, which could be harmful or not. And it can also influence the amount of light that can pass through a water sample. Light rather is important in water because you want plants to be able to grow. The total dissolved solids, because they are still quite small, if you are recycling water, the TDS, which is the total dissolved solids, will increase with repeated use of the water. And as we say, it will have a negative impact, both where it is situated, as well as when you're actually using it, particularly if you're using it for an industrial purpose. Organic matter is also going to be important in wastewater as it forms a solid in water. This solid can be undesirable when the wastewater is discharged, both because it is a solid, as well as it is a source of food and nutrients for microorganisms, which are going to lead to the depletion of the oxygen in that wastewater. The bacteria that consume the organic matter are mostly fluctuative aerobes, and this all affects the aquatic life. Some of the material, the organic matter, can also be toxic, and I've added it to this slide, but it's not necessarily an organic matter issue, but we can also have heavy metals that are present in water which are not desirable. Nutrients in the water are often needed for growth, so particularly carbon, nitrogen, and phosphorus, but they can also be harmful and undesirable to aquatic life rather. Nitrogen is an important element in biological reactions, and it can be converted to amino acids, amines, and various other organs, but we also have ammonia, which is an indicator of recent pollution, so that's the NH3. It is also an intermediate compound which can be formed during metabolism, and it is toxic to fish. The nutrients can also cause oxygen depletion rather, as well as eutrophication, which we will get to in another slide. Eutrophication can lead to the excessive growth of aquatic plants to levels that can interfere with the desirable use of the water body. Eutrophication is thus associated with the growth of algae as well as aquatic plants, water discoloration, odor, and oxygen reduction, as well as the death of fish. In terms of the bacteriological measurements, again, I'm not going to worry about this in terms of numbers and testing you on how to calculate this, but just so that you are aware of it, there are various measurements when it comes to bacteria and microorganisms. There are firstly 4 types of microorganisms that can affect water quality. So it'll be indicator bacteria, pathogenic bacteria, viruses, and pathogenic protozoa. These can transmit various diseases, including typhoid and cholera. So poor water quality and high levels of pathogens can cause illness in humans that are near that or that drink that. Many of these exist already in wastewater, and there are various different detection procedures that can happen. Commonly, though, we test for an individual pathogen. The most common is often E. coli. So if you have E. coli in the water, it can be an indicator that you have other pathogens, so not just the salmonella and these listed here, but you have other pathogens which can be dangerous to humans. So what we're going to look at next week is wastewater treatment plant design, or some more aspects of water, but some things to consider from what we've seen today. So when we want to design a wastewater treatment plant, we want to look at how do we want to include the suspended solids, SS, as well as the biological oxygen demand, and how are we going to deal with the expected pathogens. So it's 3 different things that we need to have, that we have to look at. The suspended solids are going to impact the amount of sludge we've produced, which we already said is going to be a concern generally in water that we are going to distribute out to rivers and out into the environment. So how are we going to deal with those? Total dissolved solids, heavy metals, and nutrients are also we need to test for them frequently, as well as pH, alkalinity, and hardness, because all of these items are going to be an issue with wastewater standards, as we said, for the legal side of things. Importantly, though, I'm just reading through this while I'm thinking and talking at the same time. The flow rate is going to be important when we look at wastewater treatment plants. So typically in a wastewater treatment plant, it's busy during the mornings when everyone wakes up first thing in the morning. Everyone goes to work, so there might be a little bit of a quiet time. Everyone then goes home in the evenings, and they might start up their showers, they might bath, they're cooking, so there's water flowing again. So there are definitely peak times on when a wastewater treatment plant needs to work. So this is not going to be a steady state operation. So typically, I'm not going to stay on the slide. That would be what a wastewater treatment plant looks like, and we'll get to that again next week. But what happens when we have water that isn't in a wastewater treatment plant? So we might have water, or pollution rather, that escapes and gets into our soil. So if we get groundwater that is contaminated, there are going to be 3 types of systems that we can then treat this. The first one is conventional pump and treat. There's a soil vapor extraction, and the last one is in situ bioremediation. The first one is pump and treat systems. So simply speaking, if we have water, so there's the ground surface on the right here, water or pollutants somehow get into the soil, there is groundwater, there's the groundwater level that we've got here, and there's some polluted groundwater below that groundwater level. We can sink an extraction well, and at that point of pollution, we can then pump it up, put it into a holding tank, and have some form of water treatment system, and we then have clean water. This clean water, depending on what you want to do with it, can go back into the river, can go back into the groundwater as we see fit, or off to be used as needed. The pollutant, whatever that is, depending on what it is, needs to be sent off to be dealt with, as I say, depending on what it is. The next system of how we could potentially clean groundwater, so water that has been polluted in the ground, in the soil, is through a soil vapor extraction. So the idea here is that this contaminated zone here is the gray section, or that darker section shaded bit that's there. We pump air through the soil and push any of the contaminated water into, what do they call it, an extraction well here. So there's perforations through this well. So any of the pollutants go into this well. It then gets pumped up, and it can then get discharged or sent off or treated afterwards. So this might be combined, as we got to the left here, combined with pump and treat systems. This one is typically used, I think the example here is near petrol stations. If there's a leak or a petrol leak, some volatile organics that get into the water, they are easily volatilized, that's not a word, is it? And then sent into that system that they can then get taken out of the soil. The third way of treating contaminated soil is by in situ bioremediation. So in situ, we will just design it, we will have a remediation system, which is biological, so we can have microorganisms or we can have plants doing this for us, and we will do it at the site of the contamination. So one example of this is through a constructed wetland. So we will make a constructed wetland so that if there is, or this is for preemptive rather, we can have cleaning of the water by microorganisms at the point of pollution. For this section, I'd just like to highlight that this work is again in the textbook, so Marston Eller, Introduction to Environmental Engineering, 3rd edition. Please can you understand and know everything from pages 173 to 202. So that is everything that we've done up until the soil remediation. You can then skip over the next 2 sections and go again to page 259. From there until 266, it is the soil remediation, groundwater remediation type things that we've got there. On Friday, I will hold a voluntary consultation session. So if you want to come onto Teams with any questions, please come with your questions beforehand and I can answer it to you then. If you have no questions, you do not need to come at all. Thanks.